Guys, today we're just going to go over the exam. Not going to move forward in Chapter 8 today. We'll just go over the exam. If you gave me your notes from the last help session, then please pick them up afterwards. And just wanted to go over the comments, a few things that y'all said. One thing I want to point out is that the clicker questions that y'all do in class, a lot of y'all actually said they just don't have enough time to do the clicker questions, and I understand. I know that for some of you it's difficult to process it, to get it all done, and then you're sort of stressed, like, oh, am I going to get it right, or am I going to get it wrong, or whatever. But I just want to drive home this point, that if you come to class regularly, and y'all do, like, look at this is awesome, this class, most of the students come to class almost every day. But if you do that, then you will get that 50 points. Right? That maxes out, that 50 points of class participation. It'll max out sometime between the third and the fourth exam. And then you can't get more than 50. So if you feel like you're getting every other question wrong, don't worry about it. It's not a big deal. And even if you have to miss a few days here and there, or if you have to miss a few days in the semester, that's not a big deal either. So I just want to drive that point home. Usually at the end of the semester, almost everybody has 50 points, except for that guy that's not here today. And who sits there? I mean, don't tell me. We don't need to know. But anyway, the person that's just chronically absent, that's the person that's not going to get their full 50 points. Okay? Who does sit there? No, I don't want to. We don't want to embarrass him in front of everybody. Okay. Let's see. Oh, I'm going to put a bonus question. A few of you asked for bonus questions on the test, so there's a bonus question on the test. But, you know, time is kind of tight on the test, so... But it's not a terribly difficult question. It's one that you'll recognize, but not one that you would have otherwise expected to see on the exam. What else did y'all say? Somebody said they wanted music at the beginning of class, but I always play music at the beginning of class. I don't understand. I think that's all. Anything else that was pressing you might want to discuss right now? No? Alright. I do listen to your comments. I want to know what you want to happen in the class. And I try to make that happen as best I can. Alright. The exam is 27 questions long. We will have a help session, by the way. Oh gosh, what time did I say it was going to be? 3 o'clock. And did I say Beauregard 104? Yes, in Beauregard 104. That'll be tomorrow in Beauregard 104. And it'll be a lot like what we do today. I'll go over sort of a broad outline of the test, chapters 5, 6, and 7, and then I'll answer your questions about the exams. And if you don't have questions, then we'll just sort of scroll through the exams, and they'll say, oh, I don't know how to do that. And so we'll sort of follow that tack. But if you have particular questions, you can come and you can drive the agenda for that help session if you wish. Okay? So bring your questions. The test does consist of Chapter 5. Chapter 5 is work and energy. So a couple of things you need to know how to do. You need to know how to calculate the work that's done by a force. That work, you know, the FD cosine theta. You need to know, we had several sort of conceptual ideas about work, positive and negative work, and how work can take away energy or add energy to a system. That's, by the way, that's regarding the work energy theorem, that work causes a change in energy. And we had a number of questions about that, so I would review those. You'll certainly see some questions about work changing the energy of objects. We'll need to know how to calculate kinetic and potential energy. Both elastic, that's 1/2 kx squared, and gravitational potential, that's mgh. Remember, our kinetic energy is 1/2 mv squared. You'll need to know that in the context of the conservation of energy, that is that EI is equal to EF. That's like the roller coaster problems that we did. You'll certainly see 1 or 2 or even 3 of those. They might be incorporated with other questions, but you'll certainly see those ideas come up, that the initial energy is equal to the final energy. And then you'll also see how I have work and how it affects that total energy. Okay, you'll see friction as well. Remember, friction is a non-conservative force, and it causes energy to be lost in the system. It loses energy. You need to know conservative versus non-conservative forces. I think there's just one question about them versus non-conservative forces. Conservative forces conserve energy. Non-conservative forces don't conserve energy. They lose energy. Conservative forces are path independent. Non-conservative forces, the path matters, right? The longer you go, the more energy you lose. Conservative forces are field forces. Non-conservative forces are contact forces. So you need to know those facts about conservative and non-conservative forces. I think that's it for Chapter 5. Double check. Oh, and you need to know power. This does come up on the test, all right? That power is work over time. We didn't spend that much time on it, though I think it was on the OpenStax, one of the OpenStax assignments. That power is work over time, or you can also think of it as energy over time. Okay? Then Chapter 6. In Chapter 6, we had momentum and impulse. So a couple different things that come up here. Just the idea of momentum. What is momentum? That it's a vector quantity, that you can have a system of particles that have zero momentum, but they still be moving around. We need to know Newton's second law. F is equal to delta P over delta T. And we had several questions about this, like the car running into the wall or the truck running into the tree. And what is the force imparted to that, like the dummy we did, the crash test dummy. So you need to be able to calculate whatever, what is the force involved, a change in momentum over a given amount of time. What is the change in momentum if the force acts for a given amount of time. Be able to manipulate this and calculate various things regarding Newton's second law. You also need to know how to do collision problems. That is where I say PI is equal to PF. This comes up a couple of times, at least twice, I think maybe 3 times, where you have to do a collision of a particular ilk. And collisions can be of 2 varieties. I can have 2 particles that collide up against one another, and then they move off in different directions. That's called an inelastic collision. Or I can have it where 2 particles collide with one another, and then they stick together, and they move off in the same direction. That's called a perfectly inelastic collision. You don't need to know what they're called, though you do need to know what elastic versus inelastic is, but you do need to know how to work these. You know what elastic and inelastic are? In an elastic collision, what is conserved? In an elastic collision, I always remember this because elastic, it sounds like very stretchy. Both energy and momentum are conserved. In an inelastic, bless you, only momentum is conserved. In fact, momentum is conserved in every collision that has ever occurred in the history of time, but only in a select few elastic collisions is energy conserved. An elastic collision, remember, is one where conservative forces are involved. That is field forces, mainly the collision of gas particles, because they don't actually touch. And in our solar system and other celestial bodies where you only have gravitational forces, those are elastic collisions. Things don't actually touch in those. Okay, I think that's it for Chapter 6. And then Chapter 7, you need to know your angles. All right, so you need to, like the clock problem that we did, where he said, what is the displacement of the clock? You need to know your unit circle, or it will help you to know your unit circle. You need to be able to convert between the different systems, revolutions, radians, and degrees. And then you also need to know kinematics. They're not going to be real complicated problems like we had in, say, Chapter 3 with projectile motion, but they'll be just using those two kinematics equations. The hard part on this, I think, is knowing what omega, theta, and alpha are. Just getting those situated in your mind right with the right words. That theta is displacement, omega is velocity, and alpha is acceleration. Okay? So you need to know how to work those kinematics problems like we've done in class and like you've done on the OpenStax assignments. By the way, there are, I think, 10 to 12 OpenStax questions on this test. What? That's almost half the test. And they're questions that you have in your possession. What's that? All right, so just be aware, I've given you a lot of OpenStax questions, but I've also given you simpler OpenStax questions. I know that they're difficult when you don't know how to do them, but once you know how to do them, they're not that difficult. So really focus on those in the next few days. Almost half your exam is from that. Mackenzie? Right, 5, 6, and 7. You had 3 separate assignments. But that's a lot of questions because you had 25 on this most recent one, and I think like 12 or 13 on the previous one, and something like 10 on the previous one. So there's a lot there to pull from. Okay? All right. No right-hand rule business. All right? Remember the whole business with the fingers and the thumb and all that? No right-hand rule. But you do need to know how to do kinematics and then centripetal forces and acceleration. And that's it. All right? Okay, so is there a particular topic that you would like to look at? Or is there a particular exam that you would like to look at? With the collisions of particles? Yeah, so an inelastic collision is one where they touch. So, yeah, so this is an inelastic. This one's also inelastic, but it's perfectly inelastic. All right, an inelastic is where they touch because they lose energy when they touch. A perfectly inelastic is just where they stick together and move off in the same direction. Okay. Yeah.
Okay, so alpha and theta, what's like the actual word for this velocity?
Oh, omega. So theta is displacement. That's your angle, right? And theta, right? That's sort of what we use for angle. So you probably know that already. Omega is velocity, and then alpha is acceleration. It's easy if you know the Greek alphabet, actually, because alpha is the first letter in the Greek alphabet, and omega is near the end of the Greek alphabet, just like phi. So if you know your Greek alphabet, then you should know these. Y'all know your Greek alphabet? So. Remember saying the Greek alphabet song? I have sang it for you. Do you want me to do it again? No, I'm not going to do it. It's just showing out then, because you've already heard me do it once. Okay? All right. Questions now. Particular questions. Yeah, Mallory?
So on my test due tomorrow, they have a lot about like linear versus like...
Isn't it due tonight?
Yeah.
Okay, it's due tonight. Midnight, that's basically tomorrow.
So like a lot that's like linear versus
Mm-hmm. Units will help you a lot. So when you're looking at units, and by the way, those problems are usually using this suite of equations, S equals theta r, V equals omega r, and A equals alpha r. Anytime you're relating angular to linear quantities, you're going to be doing something like that, where you're converting them based on the radius, right? Like there was one where a car was traveling and it gave you the linear speed of the car and it asked you what was the angular speed of the tire, something along those lines. You'd use that because the tangential speed on the tire is the linear speed of the car. You realize that? You follow what I'm saying? If I have a tire that's going around at some omega, a point on the tire has a certain linear speed. That is the linear speed of your car. Okay? So your question was, how do you sort of discern between V and omega and all that business? Like I said, I think units are the best way, and units really will be your friend on this test. V would be in meters per second, and omega is going to be in radians per second, or revolutions or degrees. Does that answer your question? Does that help? S? Oh, S is our arc. So if I'm looking at a piece of pie that has an angle theta, S is this distance. It's the arc. Or you could call it X if you want, or D. It's a distance in meters. Okay? Be careful on these, because you'll never go wrong converting to radians. But when you're using these equations, you have to be in radians. However, when you're using these equations, omega equals omega naught plus alpha t, or theta equals omega naught t, these can be in radians, or degrees, or revolutions. It doesn't really matter what they're in. But if you follow your units as you work through these, like for example, if I put in radians per second and radians per second squared, I'm going to get radians per second out here. But if I put in revolutions per second, I'm going to get out revolutions per second. So whatever you put into it, you're going to get out. So just be careful with that. But as you're relating your linear to your angular quantities, you have to use radians. Okay? That's also true if you're doing centripetal force. This actually isn't on your equation sheet, but we did it in class, where if I do my centripetal force like this has to be in radians. Anytime I'm building on units, I have to use the SI unit. And when I say building, I mean I'm taking these units and I'm building up newtons. These have to be in radians. Units can't, if you're good at units so far, they'll help you on this exam. Okay? You can limp through without knowing units so well, but you'll do better if you know your units. Other questions? Particular? Yeah, the formula sheet is on the test. It'll actually be on, is that what you asked? It'll be on the back side of your form. Alright, so usually students flip it over and look at the formula sheet while they're writing their answers, and then they'll bubble up the form as they are done. Jordan? Whatever is on the formula sheet on the website, which is also the same as what's in the back of your book. I don't think that it is on there as a separate equation, but the centripetal force is on there. But the centripetal force, remember, F equals ma, so this is our centripetal acceleration right here. So don't bother memorizing it. It's there. Okay, it's embedded within that centripetal force. And there shouldn't really be anything you need to memorize except for maybe your unit circle. It's all about using the things that I did do. Alrighty? Questions? Look, I'm sorry. Okay, you want me to pull up some old exams and we'll look at them? That's what I intended to do anyway. Let's see. Let's go to the back of your book, because I know you all have that, and we'll look at ones that we haven't done so far. We've done some of these as we've been practicing. let's look at this one first. I wanted to show you. This is chapter 6, actually. I just want to drive home this point, because you'll certainly have to do one that's, not exactly like this, but where you have to figure out either what is the change in momentum or what is the force involved. I just want to point out something, because this is a problem that students often have. Here, in this problem, I want to know what is the change in momentum of the ball. That is, what is delta P? And it's going to be mvf minus mvi. Anytime I'm doing a change in something, it's always final minus initial. And so here I have, I like to draw a picture. So I have this ball that's traveling at 6 meters per second. And then it's hit by a bat, and now it's traveling at 14 meters per second. And so you realize now that one of them is opposite the direction of the other, though I haven't given any signs. And so you'll need to account for the signs in these, and so be very careful. Let's take the final to be positive. So actually I'm going to do it the opposite. I'm going to call this positive and this negative, and I'll show you why in just a second. That's not usually the way we do it, the way I drew it. Draw it correctly. I'll make this positive 14 and this minus 6. So you hit it at negative 6 meters per second, or rather it comes to you at negative 6, and then you hit it at 14. And so this is going to be 0.1 times 14 minus negative 6, which is going to be 0.1 times 20. My point is that when you come to these problems, when you're changing direction, while you're taking the difference here, it's always going to be a sum, because you'll always be taking the negative of a negative number. So when you encounter one of these impulse problems, it's always going to be the sum of the initial and the final velocity, which is really the difference, but they're changing directions. Okay? So this would be 0.1 times 20, which is 2. And now if I wanted to know what is the force, I don't want to know that here, but if I wanted to know the force, then I would have to know the time in which this occurred, and so I could find delta t. Alright, so if I knew delta t, I could find F. That's what people do when they're trying to reconstruct accidents and the like. They look at how the velocities changed, and then they can reconstruct what the forces were that were involved. Okay, let's go back up ways. Okay, energy questions. We've done several of these, like number 2, but you'll certainly see some that are similar to that. In those, make sure that you ask yourself, what type of energy does this object have at this point, and what type of energy does it have at this point? Okay? Any of these stand out to you guys? Number 1? Sure. All right, I think we looked at one that was similar to this not long ago. Yeah, but let's look at it again. It's a good question. It takes 100 meters to stop. That means that some force acted over that distance of 100 meters to take away the energy on an object that's moving. That object was moving at 25 meters per second. Now, if the same object is moving at 50 meters per second, how far is it going to take? Well, first of all, you know it's going to take farther, right? Because it's going faster. So I can get rid of this one. So it's either 100, 200, or 400. In fact, it's probably going to be more than 100 too, right? You can reason that just because it's going faster, it needs a greater stopping distance. Since it's going twice as fast, at twice the velocity, the kinetic energy, which is 1/2 mv squared, it has 4 times the kinetic energy. And since this work is equal to our change in kinetic energy, and since I've increased the kinetic energy by 4, I have to increase the work by 4, so I have to increase the distance by 4. Well, whereas it was 100, now it has to be 400. Our quadratic relationship there. Any of these stand out to you guys? If you look at number 8, this is an elastic potential energy problem. This one's a little more straightforward than some of the others. I just want to know what is the elastic potential energy. This is on your equation sheet, but it's 1/2 kx squared. And the potential energy then is going to be 250 times, or half of 250 times x squared. Oh, wait, no, I'm sorry. This is not a trivial problem. So I don't know x. I want to know... I'm sorry. Let me rewind for just a second. I haven't read the problem correctly. Make sure when you get the test that you read the problems carefully, okay? Here I have a car that's moving along, an object that's moving along, and then it encounters a spring, and then it compresses that spring and stops. And I want to know how much energy does it have when that spring is compressed. Look, the total amount of kinetic energy that the car has is all transferred into the spring here. And so whatever my kinetic energy that's in the car is transferred to elastic potential energy. I want to know this quantity, but I can calculate this and I'll find that potential energy. So I just say 1/2 mv squared, 1/2 of 10 times 5 squared. That's 5 times 25, or 125, 130 joules. You're not going to see any like number 9. No Hooke's law stuff. We didn't really spend that much time on it. Okay? Any of these stand out to you guys? We're looking at them? This page? Or the next page? What? Number 10. Okay. This one looks different, but it's actually quite similar to what we've done before. I want to know how many bullets of mass 0.025 kilograms will have to be fired off to give the car a forward velocity of 0.5 meters per second. So my car is here. I'm firing a gun. So I have these bullets that are going off in this direction. And I want to move the cart in this direction at 0.5 meters per second. This is kind of like the Amy and Gwen problem where they were standing on ice and they pushed apart. One of them went one direction at one speed and the other goes the other direction at a different speed. And those speeds are different depending upon what your masses are. The bullet over here has 0.025 kilograms. The cart has 62,500 kilograms. And I want its speed to be 0.5 meters per second. And these have a speed of 250 meters per second. What's different in this problem is that it's going to take multiple bullets leaving the car to get it up to that speed. And the way you would treat that is you would say that the initial momentum is the final momentum, that they're equal. The initial momentum is initially 0. That's because it's not moving. That's the car and the bullet. And then that's going to equal to the final momentum, which is 62,500 times 0.5 minus, or excuse me, plus rather, 0.025 times negative 250. But then I'm going to put in a value n here. And the question is, what is n? Because each bullet will contribute a little bit of momentum to the system, and you want to figure out how many bullets that is. Okay? We haven't really worked a problem like that, but you'll certainly see momentum problems. Where? Yeah, you can set them to equal. Yes, you can do that. But be careful, though. She asked, can you just set these to equal to one another? This value and this value. But be careful, because sometimes the initial momentum isn't 0. That's only true because this is 0. Sometimes you have to account for, and you will on the exam, the initial momentum. It'll be non-zero because the object will be moving. I know you know how to do that, but just be careful with that. Okay? I don't know what the answer is, but does anybody know? 5,000. So you solve for n and it comes out to be 5,000. Okay? Oh, look, here's another one of those problems where you remember you add the velocities, you don't subtract them. So really you're subtracting them but one of them's negative, so you're subtracting a negative number. Okay, folks? Okay with number 11? You'll certainly see one like number 11, either perfectly or not perfectly inelastic. Okay. We've done a lot of these, but anything stand out here? We can look at some other exams. All right, let's go to some other exams. That was fall 15, so we'll look at fall 16. Usually on the old exams, that's going to be exam 3. Looks like that's the case here. If you come upon anything with torques or moment of inertia, not going to see any of that stuff, okay? So anytime you see torques or moment of inertia, know that you've gone too far. Is this the same exam? Or is it just similar?
Similar.
Okay, it's just similar. All right. Which of these I want to work through? Let's look at some. Let's start with the rotation. We can come back to these others, but let's look at the rotation first. All right. There's one of the clock problems. This is just a conversion problem. This is converting your angular to your linear. Finding your centripetal force. Thinking about your kinematics equations. This is about your sines. What's that? What's that? What did you say?
I was just telling you to stop. But
Oh, thank you. Okay. Want to work any of these people? Yeah. But I don't have to make one up. I'm sure there's one in here. Like this one? That's the same problem. Like where it started moving, what do you mean? Like where it's moving in the beginning? Yeah, I can make one up. That's how I work this one now. All right, so let's say that I have two cars. This one's 1,000 kilograms, and then I have another that's 500 kilograms. I would say it's a motorcycle. Wow, it's a little bitty car. I can't draw a motorcycle. Anyway, they're both traveling in this direction, say 30 meters per second and 5 meters per second. And the car rear ends the little car, and then they move off in the same direction. Like they continue moving, they connect with one another. And I just want to know what is the speed of these cars when they stop, or when they continue going rather. And so I would say Pi is equal to Pf. So that's going to be 1,000 times 30. That's the momentum of the first car, plus 500 times 5 is equal to, since they stick together in this case, it's going to be 1,500 kilograms times the final velocity, because they're going to move at the same speed. So that's 30,000 plus 2,500 divided by 1,500. That'll be my final speed, Vf. You'll certainly see one like that. I gave you one that has a figure in it, kind of like the one we saw in that previous exam. And then also I gave you one that's just in words. So you'll need to be able to translate the words into a physical scenario. Is that what you meant, Claire? Yeah, you know how to do that. Oh, okay. I mean, I can show you, but it works a lot similar to this. Let me just show you. I think, Like let's say that I have a car and it just shoots one cannonball, right? It's 1,000 kilograms. It shoots out a 10 kilogram cannonball, and its initial velocity, say it's moving at 10 meters per second. So it's moving in this direction at 10 meters per second, but then it shoots the cannonball, so now it's going to be going faster. All right, so we would say the initial momentum of this system is just equal to 1,000 kilograms times 10 meters per second. Actually, if you're being clever, you'll see that it's not actually 1,000 here, it's what? Before I shoot the cannonball, 1,010. But it turns out that 10 kilograms is not going to make a big deal because it's so small. But so I'll just keep it at 1,000. And then the final momentum is going to be the momentum of the whole system. That's 1,000 times VF minus 10 kilograms. We'll say this is 100 meters per second times 100 meters per second. You would set those two equal and find the final velocity. It's going to be more than 10, right? So you'd have 10,000 equals to 1,000 VF minus 1,000. So that's 11,000. So VF is 11 meters per second. Is that clear? That's what you meant, I think, right? But you still worked them the same way as you did those others. I think there are at least two of those momentum problems, collision problems, that is.
So if I could use the M1, V1, and 2,
That's all you're doing.
one just zero.
Yeah. In fact, if you just want to start with that, M1 V1I plus M2 V2I is equal to M1 V1F plus M2 V2F. That's always the equation that you're starting with. It's just that some of these are going to go to zero, and often they do. Like in the first problem that we did where everything was standing still, this whole side was zero. And then we set these two equal one another because they were equal and opposite. Okay, folks? Momentum, I really like momentum because the concepts are fairly simple for the most part, and the math is also not that difficult compared to like forces and vectors and all that business. So, okay? Yeah, no,
So, we do calculation for like most of the momentum.
all of our collision problems you can use this.
And
Yes,
just set whatever non-momentum.
absolutely.
So the only thing that matters is the direction of the velocity.
Yeah, you have to be careful with your signs, so make sure you get your plus and minus signs correct. Okay? All right, let's look at some more. Any of these rotation problems you want to look at? Which ones? You want me to pick one? Okay. Well, let's look at this number 22. You're going to have to do these, I'm fairly certain. I'm relating my linear velocity to angular velocities. So anytime you're doing that, note that you're going to have to do this. V equals omega times r. Right? I'm given V, that's 200 meters per second. I want to know omega, and r is 25 meters because the diameter is 50. This would be 25 meters. And so omega is equal to 200 divided by 25. That's 8. But 8's not the answer, right? 8 is actually in radians per second. Watch your units because I'm asking for it in revolutions per second. And so I convert this now to revolutions. 2 pi radians, 1 revolution. 8 divided by 2 pi, that's 4 over pi, 4 over 3. The answer's not here. I think there was a mistake in this one. I had 50, right, as the radius. So really this should have been radius. So this would have been 50. This would have been 16. That's 8 over pi. Well, that's not on there either. I don't know what the answer is. But you work it that way, okay? What's it supposed to be? Yes, what's that? Oh yes, okay, yeah, this would be 4. And that's 2 over pi, which is 0.64. Thank you. The SI unit for omega, theta, and alpha are all in radians, right? And so anytime you're using this, you need to make sure it's in radians. Now, you'll never go wrong with it in radians, but sometimes I don't ask for the answer in radians, and sometimes it's not necessary to convert it to radians. When you're dealing with those kinematics equations, really, is the only time. Okay. What else, folks? We have time for a few more questions. Yeah. All right. Yeah. Yeah, that's... Which chapter, Allie? What page is it on? Oh, I don't have the same page numbers as y'all, I don't think. This one? Number 2? Oh, yeah. So, this sort of draws back to what we did before, where I have a projectile, and I want to know what is its kinetic energy up top, but I need to know its velocity, and that's going to be v naught cosine theta. Don't worry, I'm not going to draw back to any projectile motion from chapter 3 or whatever. But in this one, that's what you had to do. You had to find the speed of it up at the top of the trajectory. So that's going to be 40 times cosine of 30. And then you do your kinetic energy, which is 1/2 mv squared, 1/2 of 0.15 times 40 cosine 30 squared. And then that would be the kinetic energy at the maximum height. Okay? You could find its maximum height, by the way. Oh, wait, no, never mind. No, never mind. Yeah, I get 90. You might not be, make sure you do 40 cosine 30 first, and then square that quantity. That might be what you did. Okay. If you want to see me afterwards, I can take a look at it. All right, folks. Other questions? Oh, what maximum height does it reach? Well, you want to think of it, let's sort of take it back to a problem that you'll see on the test, because you're not going to see any projectile motion. But say I throw an object up into the air at a speed of, say, I don't know, 40 sine of 30 meters per second. I throw it up at that speed, and then I want to know how high does it go up. Then I compare the kinetic energy down here to the potential energy at the top. That's how you solve this problem, actually, because this is the speed of the object in the y direction. So that's what you're concerned about, the velocity in the y direction. and whatever kinetic energy it has sort of in the y direction. The kinetic energy is not in any direction because it's a scalar. But the energy that it has due to this speed will take it up to this height. And so you would say 1/2 mv squared equals to mgh. The masses cancel. I get 1/2 of a 20 squared, that's 40 sine 30, equals 10 times h. So h is 20. Okay? But again, no projectile motion. You're not going to see any of that. All right? Any other questions about the test? How y'all feel about it? Can't get a thumb on you. Y'all feeling okay about it? I think, listen, let me warn you and encourage you that I think that this material is probably the easiest material that we've had all semester. We don't agree? I think that's true. But there's also a lot of it, so there's just a lot to internalize. Here? I'll do it. Like nobody else. But when you want it until tomorrow night? Yeah, that's fine. I'll extend it until tomorrow night. It's not just for you, it's for everybody. Y'all have a good day, okay?